Alright, so again, what we're going to be doing today is we're talking about linear polynomials, okay? So, this is what your textbook would give you as a definition of a polynomial. Is that pretty? Pretty ugly, right? Okay. What on earth is that saying? So what I want to do is let's walk through it and try to help you understand it. Because there's going to be a time where you're in like a math class or some other class, and they'll give you something like this, and you have to figure it out without someone explaining it to you. So, let's go through it. Let n be a non-negative integer. Okay, pause right there. Let's look at this. Where do you see n? Where is it? In that top part, you tell me, which is the exponent. Thank you. So, what we have here is n is in the exponent, and what does n have to be? Good, non-negative, which is positive, right? Okay, so I'm going to put some notes here. So non-negative tells us it needs to be positive. Okay, what does integer mean, guys? An integer is just whole numbers, right? Now, an integer could be positive or negative, but what did this just say? It has to be positive. So what this is telling us right now is that a polynomial, if you look at the exponents, you're going to see positive whole numbers. So basically, we're not going to see anything too crazy. So first thing is that our exponents are positive whole numbers. And what I need you guys to do throughout this year, A, check my work. A lot of times I make mistakes because I'm thinking ahead. But B, if you can't read something that I'm writing, you can ask. I don't have the best handwriting, especially when I'm like trying to write like this, but whatever. Okay, so what do we know about polynomials? The exponents are positive whole numbers. And let A, A1, A2, those are the numbers out in front. What do we call those? Coefficients. Good job, okay? So the coefficients, they don't have to be integers. They can be real numbers. Real numbers means it can be rational or irrational. Irrational meaning it can go on forever, whatever. It can be fractions, whatever. Okay, just a couple of things. The highest exponent, that is called your degree. That's going to be important as we go forward. The leading coefficient is this guy right there. That's going to determine some important things, so it's good to know that. Okay, now let's just do a little practice here. Here are four kind of equations, four functions. What we want to do is figure out which of these are polynomials and which ones are not. Using our definition said that to be a polynomial it needs to be positive whole number exponents, and the coefficients are just real numbers. So, I want you to work with the people around you, and with these four, give me, are they a polynomial or not? Okay, you've got a minute, figure that out. It's really quiet, so what are you doing right now? You can talk to your neighbors. A, B, C, D. Is that a polynomial or is it not? That's all you got to do. Now, if it is a polynomial, we're going to state the degree and the leading coefficient. Okay, let's actually just start with A. What I want you guys to do is give me thumbs up or thumbs down. Polynomial or not a polynomial? Thumbs up, polynomial, thumbs down. What do you think? Okay, I got a lot of people not voting. Does that mean we don't understand? Let's just go through it, okay? In order to be a polynomial, what do we have to see, guys? Exponents that are positive and are whole numbers. On this, are the exponents 3? Is that a positive positive whole number. Okay, so is this a polynomial? Yes, because it's made up of positive whole number exponents, and the coefficients are real numbers, so they can be fractions. That's okay. So A was a polynomial. We liked it. But what about B? Is it a polynomial? Thumbs down. Tell me why. There you go. We have a negative exponent. We don't like negatives. So this one would not be a polynomial, okay? Now, excuse me, one thing it says on here is that if it is a polynomial, we need to state the degree and the leading coefficient. The degree, as we saw in the last one, that is our highest exponent. So I'm going to put a little note here. That is the highest exponent. So on part A, what is our highest exponent? 3. So I want to put the degree is 3. The degree is 3. We would call that a cubic. Yeah, maybe you haven't learned that yet, and that's okay. The leading coefficient is going to be the number out in front of that term, which is what? 4. Good job. Alright, is that making more sense? What we're doing, is it a polynomial or not? Looking at C, what do you think? Give me a thumbs up, thumbs down, or if you're in the middle, if you're like, I don't know. Okay, we've got a good mix on here. I've seen a lot of thumbs up and a lot of thumbs down. I think we're seeing some thumbs up because we're looking at 4 and 2. Are those positive whole number exponents? Yes, but what else is going on here? Square root. Oh, those are ugly. Okay, secondary 2, you learned that there's a different way you could rewrite that. You could write it as a rational exponent, meaning x to what? 1/2. You remember that? Is that going to mess up our positive whole number exponents? Yes, so this one is actually not a polynomial. Polynomials are nice and pretty looking, and this square root is just kind of ugly, and that makes it not a polynomial. Now, if we could simplify it, then that would work, but we actually can't simplify on that one. Okay, let's go to D. Last one. What do you guys say? Thumbs up or thumbs down? Do we have positive whole number exponents? Yes, we have a 1 right here, and then we have a 4, so that is a polynomial. Now, what about the degree? Is the degree the first exponent we see? It's the highest, so this would be 4. And that would be quartic is the name we use there. And as far as the leading coefficient, that's going to be the coefficient of the degree, of the one with the highest, so that would be -2. Okay, so all we did on that was we were deciding, is it a polynomial or is it not? Okay? Do you have any questions on that slide? And if you do, please ask, because what I've learned is most of the time, if you have a question, someone else does. Okay? If not, we'll keep going, but any questions? Okay, so these are different types of polynomials, okay? We'll start off with the 0 function, which is 0. That's all that's going on there. We won't work with that a lot because it's just 0. A constant function is just a constant. It's just a number. So it could be something like f of x is 2. Pretty boring because it's just the same value the whole time. It's just 2. What we're going to work with today is the linear function. That's where our degree is 1. We have a variable with the exponent of 1. Next time we're going to talk a lot about quadratics. And most of this should be reviewed. I think you did a lot of linear functions in 9th grade. And you did a lot of quadratics in 10th grade, or if you're a year ahead, whatever. But secondary 1, secondary 2, so this will just be a review for you, okay? So let's talk about linear functions. Do you remember y equals mx plus b? So, fun story. I actually graduated from Hunter High. When I was a sophomore, my teacher was Mrs. Allen. How many of you had Mrs. Allen? Alright, so we can relate because I had her too. She would always get mad at me because I didn't show work. She'd always say, you show your work. So what I would do is on every problem I would write y equals mx plus b, then I write the answer and circle it. It's like, that's not showing work. I'm like, hey, it's something else. So anyway, what is y equal to mx plus b? It's the equation of the line. This is called the slope-intercept form of the line because what does it tell you? The slope and the y-intercept. M is our slope. And I was told that because a French word for slope starts with an M. I don't know if that's true or not, but let's go with it. B is your y-intercept. This is the way I like to represent lines. There's also point slope form, which I believe is going to be on another one, but if not, I'll write it in for you, okay? Now, help me out here. What does slope stand for? Or like, what does it even mean? Was that, you know it's hard, it's like with masks, I can't tell who's talking. I hear voices, but yeah, tell me your name first. Josh, what is slope?
Rise over run.
Good job, that's a rise over run. And based off slope, we can tell the steepness. If it's positive or negative, we can tell if it's going up fast or if it's going up slow. Or down fast or down slow. Now our actual formula for it, I'm going to write it here because it's going to show up. The rise is going to be the change in our y values. So this little triangle here, that's delta, it means change in our y values. And the run is going to be the change in our x values. So we're saying, how much is it changing in the y, that's the rise. How much is it changing in the x, that's the run. And this is where we came up with the formula of slope. The slope is y2 minus y1 over x2 minus x1. Is this ringing bells? You've done this before, nothing new here, just need a little refresher. And then B, that's just your y-intercept, that's pretty easy. Just where it crosses the y-axis. Alright. Now let's, I'm going to go back actually. Let me show you the other form, it's called point slope. So I'm going to change this. So point slope, instead of slope-intercept, it gives you a point and the slope. The equation is y minus y1 equals mx minus x1. So this is another way you could write the equation of a line. The difference is with slope-intercept, it gives you the slope and the y-intercept, and for point slope, it gives you the slope and a point on that line. So the slope would be m, but then it has a point x1, y1. That's a point on the line. So those are the two formulas we're going to be using here. Now, which one do you use? Well, you could use either. It really depends on the one, okay? The type of problem we're doing. So let's go, sorry, was everyone done writing this? All good? Let's go to a problem here, okay? Write an equation for the linear function f such that f of negative 1 is 2 and f of 3 is negative 2. This is just a fancy way of saying when I plug in x to the equation, what does it spit out? Or, sorry, when I plug in negative 1 for x, what does it spit out? 2. So a point on this line is negative 1, 2. So I'm going to come over here and negative 1, 2. There is a point. So then, let's do the same thing. If I plug in 3, it gives me negative 2. So it tells me the point 3, negative 2. There's the other point. So I'm given these 2 points, and it says, write the equation of the line that goes through those. Now we've got two equations. We could use slope-intercept and figure it out that way, or we could use point-slope and figure it out that way. Does it matter which way we do it? What do you want to do? You tell me. Choose your own adventure. Slope-intercept. I think that's easier. We're going to do both, actually. So let's start with y equals mx plus b. to do is I'm going to try to connect those dots. And I'm not the greatest artist, but I'll do my best here. So I believe if I were to connect this, it's going to look something like that. Does that look about right? Okay, I want you to turn to your neighbor group people and figure out, we need to know the slope and the y-intercept. So based off our line, what would be the slope and the y-intercept? Talk to your neighbors, and I'll come back to you in 20 seconds. Really? Did I already call on you? Really? Alright. I'm going to call on you to start with. Okay, so let's come back, guys. Brinley, I want you to explain how you got the slope, and then let's show you how you got the y-intercept. So Brinley, how did you figure out the slope? So let me write that. So if we're looking at the slope, the change in y is it's going down 1, and then it goes over 1, so that would be 1. Right? What do you guys think? Yes, but we're missing one little thing that makes a big difference here. There we go. Alright, so if it's going down 1, we have to signify that by the negative, so the slope is negative 1. Alright, there we go. Thanks, Brinley. Okay, Lashaya, what about the y-intercept? Where are you, Lashaya? There you go. Sorry, I couldn't see your hand. How do you get the y-intercept here? Man, you have a very quiet voice. I can't hear what you're saying. What do you think the y-intercept is? If we're looking at where this line crosses the y-axis, so right here, this is our y-axis. It looks like it crosses it at 1, right? Now that works out pretty good for us. We're just going to say b is 1. So our equation here is y equals negative x plus 1. Is that what you guys came up with? Okay, now, to be honest, we got lucky here because it was a nice equation, but a lot of times these have fractions. So I want to take a second and show you how you would do this using your point-slope form. Okay? Takes a little more work, but it's easier for the harder ones, okay? How would we figure out the slope if we were doing point slope? If we didn't just say it goes down 1 over 1. What we would have to do is we'd come up here and say, alright, I'm going to label this as x1, this is y1, and this is x2 and y2. And we're going to have to use a formula that we used earlier for slope, which was the change in y over change of x. So if I'm doing slope is y2 minus y1 over x2 minus x1. Now I've labeled those so I can plug those in. So I'm going to go and take y2 minus y1. That's going to be negative 2 minus 2. Then we're going to take the x2 minus x1. That's going to be 3 minus negative 1. And when I do that, I get negative 4 over positive 4, which is negative 1, which we got, right? So that means we did it right for this slope. Good job. Now, as far as getting the equation, what we're going to do is plug that into our point-slope formula. If you remember, our point-slope formula looked like this. We did y minus y1 got the slope now is -1. And we already have an x1 and a y1, so let's go and plug those in here and see if we get the same equation we came up with before, okay? Let's see, so this would be, how am I going to do that? So this will be y minus y1, so that's y minus 2, is equal to -1, and then x minus x1 is going to be x minus a -1. What happens when we get those two negatives together? There we go, that'll be a positive. There we go, is that better? Can you see that a little easier? Okay, so what we get here is y minus 2 is equal to -1, and this will be x plus 1. Because two negatives make a positive. I'm going to distribute that negative, so I get y minus 2 is equal to a -x minus 1. And if we're going to just solve this for y, what should I do? Add 2. When we do that, we get y equals -x plus 1. Isn't that what we got before? Voila, that's how you do it for maybe one of those more challenging ones, but either way works, right? So you can choose whichever one works best. Okay, any questions on that problem? Is this very challenging? This is stuff you did in like when you were a freshman, okay? Or, I don't know, some of you, yeah, whatever, let's just keep going. So now, what this is actually, our formula for slope is just a fancy way of, okay, sorry, back up. This is your equation for the average rate of change. Have you ever heard that before? Average rate of change. It sounds pretty like technical and really complicated, but it's just slope. If we were to look at our formula for slope and compare it to what we have here, it's the same idea. Slope, you just do the change in y over the change in x. Well, instead of looking at x and y's, if we just look at this in function notation, so instead of y we have f of x, this is basically the same idea. Average rate of change is slope. Now where this is actually, we're going to use this formula as you get into calculus to look at the average rate of change in quadratics and in cubics, and that's where it gets a little more complicated. But it all stems from this basic idea of slope. Okay, we're going to do just kind of a story problem here. Nothing too crazy, it's actually pretty easy, but we need a reader. How about Arlette? Will you read that for us? Depreciating. Okay, so we're going to buy this building for $50,000. And it's going to be depreciating by $2,000 each year. It's kind of like when you go out and buy a car. If I spend $50,000 on a car and I drive it off, can I ever sell it for $50,000 again? No, because then it's used and it drops in value, and then using it, yeah, it's depreciating